Before electricity, machines already ran the world. Long before wires, motors, or power grids, societies depended on systems that converted natural forces into reliable work. These machines powered food production, manufacturing, transportation, and timekeeping for centuries. A machine was never defined by electricity. It was defined by motion, control, and repeatability. By the 1st century BCE, water mills were already operating across the Mediterranean world. Roman engineers expanded them into large-scale systems, using flowing rivers to grind grain continuously. By the Middle Ages, thousands of water mills operated across Europe. They formed the backbone of local economies. These machines did not switch on or off. They worked as long as nature allowed. Wind power followed a similar path. By around the 9th century, vertical windmills were documented in Persia. They captured wind to perform real mechanical labor. Over time, wind-driven machines spread across Europe. They drained land, ground grain, and powered workshops. What mattered was not the energy source, it was the system built around it. Gears transferred motion, shafts distributed power, governors controlled speed. Entire production chains operated without electricity. They relied only on gravity, wind, and flowing water. Precision also existed without power. Mechanical clocks in medieval Europe regulated motion. Escapements converted falling weights into controlled time. These systems made coordination possible long before electronic signals existed. This world was not primitive. These machines were visible, repairable, and reliable. When something failed, the cause was physical. Power could be seen, heard, and felt. Electricity did not invent machines. It changed how power was delivered. Before switches and outlets, machines already shaped civilization, quietly, continuously, without interruption. That world worked, not because it was simple, but because it was engineered to survive without electricity.
Before electricity, water was the most reliable engine humans ever built. Long before coal, oil, or power grids, flowing water provided continuous, predictable energy. Unlike muscle or wind, it did not tire and did not need to be stored. It simply moved, day and night. By at least the 3rd century BCE, water-powered machines were already being used in parts of the Hellenistic world. But it was the Romans who turned water power into a true system. By the 1st century CE, water mills were grinding grain across the empire, converting rivers into mechanical labor. These mills worked on a simple principle. Flowing water turned a wheel, the wheel turned a shaft, the shaft powered work. Over time, this logic expanded. Vertical wheels captured fast-moving rivers. Horizontal wheels worked in smaller streams. Gears translated rotation into useful motion, driving millstones, hammers, and presses. By the early Middle Ages, water mills were everywhere. In parts of Europe, entire regions depended on them for food production. A single mill could replace dozens of laborers, operating continuously as long as water flowed. Water was not just a resource, it was infrastructure. Long before electricity, rivers powered civilization, quietly, continuously, and with remarkable efficiency. And for centuries, that engine was enough.
Before electricity, wind was more than weather. It was a working force. Long before engines and turbines, societies learned how to turn moving air into controlled mechanical power. Unlike muscle, wind did not tire. Unlike fire, it did not need fuel. It arrived freely if systems were built to capture it. By around the 9th century, vertical windmills were documented in Persia. These machines were not symbolic. They were practical tools, built to grind grain and pump water in dry, windy regions where rivers were unreliable. The design was simple, but effective. Walls captured the wind. Sails absorbed motion. Rotation was transferred inward to do work. As the idea spread westward, wind machines evolved. By the 12th century, horizontal axis windmills appeared across Europe. These could be turned to face changing wind directions, making them more flexible and more powerful. Windmills did more than grind grain. They drained wetlands in the Netherlands, turning flooded land into farmland. They powered sawmills, oil presses, and workshops. Entire landscapes were reshaped by machines driven only by air in motion. Wind power required understanding variability. Engineers developed adjustable sails, braking systems, and gear ratios to prevent machines from destroying themselves during strong gusts. These were early solutions to a problem still faced today: controlling unstable energy. Windmills were not constant. They stopped when the air stopped, but when conditions were right, they worked at scale. They produced food, materials, and land without smoke, fuel, or combustion. Wind machines proved something essential. Power did not need to be stored to be useful. It needed to be captured, controlled, and released into systems designed to handle uncertainty. Long before electricity, wind already powered economies, not occasionally, but structurally. In a world without power grids, time itself had to be engineered. For most of human history, time was approximate. It followed the sun, the seasons, and local custom. But as societies grew more complex, approximation stopped being enough. Coordination demanded precision. By the late 13th century in Europe, mechanical clocks began to appear in monasteries and city towers. These were not personal devices. They were machines built to regulate behavior, prayer, labor, markets, and governance. The breakthrough was control. Escapement mechanisms transformed continuous motion into measured intervals. Falling weights provided energy. Gears divided motion into predictable steps. For the first time, machines could regulate themselves. Time became mechanical. These early clocks were inaccurate by modern standards, but they were consistent. And consistency mattered more than precision. Cities could now agree on when work started, when gates closed, and when obligations were enforced. Clockwork spread quickly. By the 14th and 15th centuries, public clocks shaped daily life across Europe. Bells marked hours. Labor followed schedules. Authority became synchronized. This was not just about timekeeping. Clockwork introduced a new idea that systems could run independently once set in motion. The same logic soon appeared in mills, looms, and automated devices. Controlled repetition became a design principle. Even early automation depended on clockwork thinking. Cams, gears, and rotating drums executed sequences without human judgment. Once engaged, the machine followed instructions embedded in its structure. Clockwork changed how people thought about order. It made time visible, divisible, and enforceable. It trained societies to accept regulation by machines. Long before electronic signals, mechanical clocks imposed discipline on entire civilizations. They did not merely measure time, they created it. Long before power lines reached factories, industry already had a heartbeat. In the early stages of industrialization, electricity did not power production. Motion did. Factories were built around a single source of power, usually water or steam, and everything else depended on how that motion was distributed. By the late 18th and early 19th centuries, large workshops operated using line shaft systems. A central wheel or engine turned a long rotating shaft. From it, belts and pulleys carried motion to machines spread across the building. Power moved through space mechanically. Every loom, press, or lathe depended on its position relative to the shaft. Machines could not be placed freely. Entire factory layouts were dictated by physics. This created a rigid but efficient system. When the shaft turned, everything moved. When it stopped, production ended instantly. Workers adapted to the rhythm of the machine, not the other way around. These factories were loud, dangerous, and unforgiving. Belts snapped, shafts spun overhead. Clothing could be caught in moving parts. Yet the system worked because it was centralized, visible, and direct. Steam engines expanded this model. After the late 18th century, steam replaced rivers in many regions, but the logic stayed the same. Steam did not power individual machines, it powered motion, which was then shared mechanically. Factories became ecosystems of movement. Maintenance was constant, lubrication mattered, alignment mattered. A single failure could halt an entire operation. But these systems also had advantages. They were energy efficient for their time, they were repairable on site, and they made large-scale manufacturing possible long before electric motors existed. Electricity did not create factories. It untangled them. By allowing power to be delivered individually, electricity freed machines from shafts, reshaped factory design, and changed how labor was organized. But for decades before that shift, factories ran continuously, not on electricity, but on rotating steel and disciplined motion. Long before computers used electricity, calculation was already mechanized. As trade, astronomy, engineering, and taxation became more complex, mental arithmetic was no longer enough. Societies needed machines that could reduce error, speed work, and produce repeatable results. Some of the earliest calculating tools appeared thousands of years ago. The abacus was already in use in Mesopotamia by at least the 2nd millennium BCE. It did not store numbers, but it structured thought, turning calculation into a physical process. By the 17th century, mechanical calculation advanced further. In 1642, Blaise Pascal built a mechanical adding machine designed to assist with tax calculations. It used interlocking gears to perform addition automatically. A few decades later, Gottfried Wilhelm Leibniz expanded the idea, creating machines capable of multiplication through stepped gears. These machines did not think. They followed mechanical logic. Rotation represented numbers. Gear ratios encoded rules. Once motion was applied, the result was inevitable. This was computation without interpretation. The most ambitious designs came later. In the early 19th century, Charles Babbage proposed the difference engine, a fully mechanical machine intended to compute mathematical tables with high accuracy. Although never completed in his lifetime, its design proved that complex calculations could be automated entirely through mechanical means. These machines solved a specific problem: human error. Tables used in navigation, engineering, and finance were often wrong because they were copied by hand. Mechanical calculation promised consistency. The same input always produced the same output. Calculation became a system. Cranks replaced scribes. Motion replaced memory. The machine did not get tired, distracted, or creative. Electricity did not invent computation. It removed the physical limits of gears, friction, and size. But long before electronic circuits, calculation was already being delegated to machines, quietly reshaping science, commerce, and administration. Long before automation became a buzzword, machines were already replacing decisions. In early mechanical systems, automation did not mean intelligence, it meant sequence. Once a process was designed, machines could repeat actions without judgment, fatigue, or variation. This idea appeared centuries before electricity. By the late medieval period, cam-driven mechanisms were used to control movement in mills, clocks, and workshops. Cams converted rotation into timed actions, lifting, dropping, pressing, or releasing components in a fixed order. The machine followed instructions carved into its shape. One of the most influential examples appeared in the textile industry. In the 18th century, looms were increasingly mechanized to repeat complex weaving patterns. Human hands still guided the process, but decision-making was slowly embedded into hardware. Automation accelerated in the early 19th century. In 1804, the Jacquard loom introduced punched cards to control weaving patterns. Each card represented instructions. Holes allowed hooks to pass through, determining which threads were raised or lowered. The loom did not understand the pattern, it executed it. Change the cards and the machine behaved differently. This separation of instruction from motion was revolutionary. It allowed one machine to perform many tasks without redesign. Similar logic appeared elsewhere. Barrel organs played music automatically using pin cylinders. Mechanical clocks triggered bells and figures on schedule. Early industrial machines performed repetitive tasks with precision once activated. Automation was not about speed, it was about consistency. Machines removed variation from processes where variation was costly. They ensured that results were repeatable, predictable, and scalable. Electricity later amplified automation, but the core idea, instructions embedded into systems, already existed. Long before software, automation was mechanical, and long before machines made decisions, they followed them perfectly. In an age without electronics, machines were already being programmed. At the beginning of the 19th century, textile production faced a limitation. Complex patterns required skilled human control, and errors were costly. The solution was not faster hams, it was encoded instruction. In 1804, Joseph Marie Jacquard introduced a loom that transformed weaving. Instead of relying on memory or manual selection, the Jacquard loom used punched cards to control which threads were lifted or lowered. Each card contained a set of holes. The holes were instructions. When a card passed through the machine, hooks either engaged or disengaged based on its pattern. This determined the weave automatically. Change the card sequence, and the machine produced an entirely different design. The loom did not store information. It read it. This separation of instruction from mechanism was revolutionary. The same hardware could perform endless variations without being rebuilt. Patterns became transferable, reusable, and standardized. The impact was immediate. Textiles that once required teams of skilled workers could now be produced with far fewer hands. Complexity scaled without proportional labor. For the first time, creativity could be encoded into a machine. The Jacquard loom also introduced a deeper idea. Instructions could exist independently of the machine that executed them. This concept would later influence mechanical calculation, early data storage, and eventually electronic computing. Resistance followed. Workers feared job loss, and some looms were destroyed during early protests. But the logic was unstoppable. Systems that embedded decisions into structure were more efficient and more consistent. Long before digital code, punched cards controlled behavior. The jacquard loom did not just change textiles, it demonstrated that machines could follow abstract instructions, a principle that still governs technology today. Before timing was digital, it was mechanical. As machines grew more complex, raw power was no longer enough. Systems needed coordination. Parts had to move in the right order, at the right speed, for the right duration. Timing became a machine problem, not a human one. Early engineers solved this without electricity. One solution was the governor. In the late 18th century, centrifugal governors were used to regulate the speed of steam engines. As rotation increased, spinning weights moved outward, automatically reducing fuel input. The machine corrected itself. Speed became controlled, not guessed. Mechanical timing also relied on flywheels. Heavy rotating discs stored energy and smoothed irregular motion. This prevented machines from stalling or tearing themselves apart during load changes. Clocks contributed more than timekeeping. The same escapement logic that regulated hours and minutes was adapted to control movement in industrial machines. Motion could be divided, delayed, or repeated with precision. Factories depended on this. Machines had to start smoothly, maintain steady operation, and stop safely. Mechanical timers ensured that actions happened in sequence, valves opening, hammers striking, presses releasing. Even music relied on timing machines. Barrel organs, music boxes, and automata used rotating cylinders or discs to trigger actions at exact intervals. Timing was encoded physically, not calculated. What made these systems powerful was feedback. Machines responded to their own behavior. If speed increased, control mechanisms pushed back. If motion slowed, stored energy carried the system forward. This was regulation without sensors, no electricity, no software, no computation, just physics arranged intelligently. Mechanical timing made large-scale industry possible. It reduced accidents, improved quality, and allowed machines to run unattended. Long before electronic clocks and microcontrollers, machines already knew when to act. They did not measure time, they enforced it. In a world powered by water, intelligence could be fluid. Long before electronic sensors or digital controllers, engineers learned how to use water itself to make decisions. Pressure, flow, and resistance became signals. Valves became logic. This idea appeared early. In the 1st century CE, Hero of Alexandria described machines that responded automatically to changes in water and air pressure. His designs used floats, siphons, and counterweights to open doors, dispense liquids, and regulate flow, all without human input. Hydraulic systems worked because water obeyed rules. If pressure increased, something moved. If flow stopped, something closed. Engineers exploited this predictability. Float valves maintained constant water levels in tanks and fountains. As the level rose, a float lifted and shut the inlet. As it fell, the valve opened again. This simple feedback loop allowed systems to regulate themselves indefinitely. Cities depended on this logic. Public fountains, baths, and irrigation networks relied on hydraulic control to distribute water evenly. In large Roman complexes, valves and channels managed supply across vast distances, ensuring continuous operation without supervision. Hydraulic intelligence also entered industry. Water-powered presses used pressure to amplify force.
Hydraulic accumulators stored energy, releasing it when needed. Timing and control emerged naturally from the behavior of fluids under constraint. Unlike mechanical gears, hydraulic systems absorbed shock. They smoothed motion. They responded gradually. They protected machines from sudden failure. What mattered was not speed, but balance. These systems did not calculate numbers. They calculated states, open or closed, full or empty, flowing or stopped. Electricity later replaced water with signals, but the logic remained the same. Long before electronic control systems existed, machines already responded to their environment, using water as both power and intelligence.
Long before recorded sound, music was already automated. For centuries, machines produced music without performers, electricity, or amplification. These were not toys. They were precision systems designed to encode rhythm, timing, and melody into physical form. One of the earliest examples was the water organ. By the 3rd century BCE, engineers in the Hellenistic world used flowing water to regulate air pressure, forcing air through pipes at steady rates. Water controlled volume, pipes controlled pitch. Music became mechanical. As mechanisms evolved, control shifted from fluids to structure. By the medieval period, pinned barrels and rotating cylinders were used to store musical instructions. Each pin represented a note. As the barrel turned, pins lifted levers, opened valves, or struck strings at exact moments. The machine did not listen, it followed sequence. Barrel organs, carillons, and later music boxes encoded entire compositions into metal and wood. Once set in motion, they performed the same piece identically every time. Timing was everything. Rotation speed determined tempo, gear ratios controlled rhythm, springs or weights provided energy. The result was music regulated by physics, not interpretation. These machines solved a specific problem: consistency. In public spaces, churches, and private homes, automated music provided reliable sound without skilled musicians present. It turned performance into a repeatable process. Music machines also advanced engineering. They demanded precise tolerances, reliable timing, and durable materials. Many techniques later used in clocks and automation were refined through musical mechanisms. Electricity eventually replaced springs and weights, but the idea remained. Music could be encoded, stored, and reproduced by machines long before speakers or recordings existed. These systems proved that creativity could be mechanized without being lost. The melody came from humans, but the performance belonged to the machine. In a world without satellites, navigation depended on machines that could think in angles. Finding direction across oceans was not a matter of intuition. It required instruments that transformed the sky, time, and geometry into usable information. Long before electronic navigation, these machines made global travel possible. One of the earliest navigation machines was the astrolabe. By at least the 2nd century BCE, Greek astronomers used astrolabes to measure the height of stars above the horizon. From these angles, sailors and scholars could determine latitude with surprising accuracy. The machine worked through geometry. Rotate the disk, align it with a star, read position from engraved scales. At sea, this logic evolved. By the 15th century, mariners relied on instruments like the quadrant and later the sextant. These devices used mirrors and angles to calculate position using the sun or stars, even on a moving ship. Time mattered as much as direction. To determine longitude, navigators needed accurate timekeeping.
Mechanical marine chronometers, perfected in the 18th century, allowed sailors to compare local noon with a fixed reference time. The difference revealed position, east or west. Navigation became mechanical computation. Angles, time, and motion were converted into coordinates. Human judgment remained important, but machines reduced uncertainty. These tools were not optional. Without them, long-distance trade, exploration, and empire building would have been impossible. Errors meant ships lost, cargo destroyed, and lives at risk. Navigation machines did not move ships, they moved certainty. Electricity later automated navigation. But long before signals and screens, mechanical instruments already guided humans across featureless oceans, using nothing but metal, math, and the sky. Long before electronic targeting, warfare relied on machines that obeyed physics. Armies needed power, precision, and coordination without wires, sensors, or computers. Mechanical systems filled that gap, turning force into controlled destruction. Siege machines were among the earliest examples. By the 4th century BCE, torsion-powered catapults were already in use across the Mediterranean. Instead of relying on bending wood, these machines stored energy in twisted bundles of sinew or rope. Release the tension, and the projectile followed a predictable path. Accuracy came from geometry. Angles were set mechanically. Tension was measured by experience. Range was adjusted by structure, not calculation. Once prepared, the machine performed the same action every time. Later designs refined this logic. Ballistae functioned like giant crossbows, using torsion springs to launch bolts with remarkable precision. Roman engineers standardized components, allowing machines to be assembled, repaired, and reused across campaigns. Mechanical timing mattered in war. Reloading sequences, firing intervals, and coordinated volleys depended on repeatable motion. Winches, ratchets, and gears controlled force safely, allowing crews to operate powerful machines without injury. Naval warfare also relied on mechanics. Rams, cranes, and boarding devices used leverage and gravity to amplify human strength. Success depended on design efficiency, not electricity. Even firearms depended on mechanical systems. Before electronic ignition, flintlock and matchlock mechanisms converted motion into sparks with reliable timing. Pull the trigger and a sequence unfolded. Clamp, strike, ignite. These machines did not aim. They ensured consistency. War machines reduced uncertainty in chaotic environments. They allowed force to be delivered repeatedly, predictably, and at scale. Electricity later improved targeting and communication. But long before that, wars were fought and won by machines that relied entirely on tension, leverage, and disciplined motion. No wires, no circuits, just engineered force. In an era before electric grids, stopping was the exception. Early industrial systems were designed to run continuously. Once set in motion, machines worked as long as power flowed, materials arrived, and parts held together. Downtime was costly, so factories were built around endurance. Water-powered factories rarely paused. As long as rivers flowed, mills operated day and night. In the 18th and 19th centuries, entire industrial districts were organized around waterways, with shifts arranged to keep machines running without interruption. Steam extended this logic. By the early 19th century, steam engines allowed factories to operate independently of rivers, but steam was expensive to start and inefficient to stop. Engines were kept running for long periods, even when output slowed, to avoid waste and mechanical stress. Factories adapted accordingly. Shifts were staggered. Maintenance happened while machines were still warm. Components were replaced without shutting down entire systems. Continuous operation became a management strategy, not just a technical one. Heat was reused. Waste steam warmed buildings, dried materials, and powered auxiliary systems. Energy efficiency emerged not from electronics, but from necessity. This created a different relationship with machines. Workers adjusted their lives to mechanical schedules. Nights, weekends, and holidays mattered less than momentum. The factory became a living system that demanded constant attention. Reliability was everything. Machines were overbuilt, not optimized. Thick cast iron, slow rotation, and generous tolerances allowed systems to survive long hours and imperfect conditions. Electricity later changed this balance. Motors could start and stop instantly. Power could be delivered only when needed. Factories became flexible. But before that shift, industry learned how to survive through continuity. These factories did not run fast, they ran forever.
In mechanical systems, failure rarely came from design. It came from neglect. Before electricity, machines depended entirely on physical contact. Gears rubbed, shafts bent, bearings wore down. Every moving part slowly destroyed itself unless attention intervened. Maintenance was not optional. In early factories and workshops, machines required constant care. Lubrication had to be applied by hand. Alignment had to be checked visually. Loose bolts, cracked teeth, and warped shafts were detected through sound, vibration, and experience. There were no sensors. Operators learned to listen. A change in pitch meant friction. A shudder meant imbalance. A delay meant resistance. Maintenance became a skill passed through practice, not manuals. Downtime was dangerous. When a critical component failed, entire systems stopped. Water mills stalled, line shafts froze, steam engines lost momentum. Because machines were interconnected, a single fault could cascade across the factory. This shaped how machines were built. Components were oversized, speeds were kept low, designs favored tolerance over efficiency. Parts were made thick enough to survive abuse and imperfect care. Maintenance also shaped labor. Skilled mechanics held enormous power. They decided when a machine could run, when it had to stop, and how long repairs would take. Their judgment controlled production. Electricity reduced this burden. Electric motors isolated failure. Sensors replaced listening. Maintenance became predictive instead of reactive. But before that transition, machines lived and died by attention. They did not fail suddenly. They failed slowly, unless someone noticed. And in a world without electricity, noticing was everything.
When electricity arrived, it did not replace machines. It replaced constraints. Mechanical systems worked, but they imposed limits. Power had to be generated in one place and distributed physically. Shafts, belts, and gears tied machines together, making factories rigid and dangerous. Electricity changed that relationship. By the late 19th century, electric motors allowed power to be delivered directly to individual machines. Instead of sharing motion, machines received energy independently. Layouts became flexible. Failures became isolated. This mattered more than speed. A single electric motor could be started, stopped, or adjusted without affecting the rest of the system. Maintenance no longer halted entire factories. Production became modular. Electricity also changed scale. Small workshops gained access to the same power principles as large factories. Energy could be transmitted over distance. Location mattered less than connection. Control improved. Switches replaced levers. Wires replaced shafts. Power could be regulated precisely and instantly. Machines responded faster and with less physical inertia. Safety improved as well.
Removing belts and overhead shafts reduced accidents. Workers no longer stood beneath moving machinery. Power became invisible, but more predictable. This transition was gradual. For decades, electric motors were added to existing mechanical systems. Hybrid factories emerged, combining shafts with wires. Only over time did fully electric layouts dominate. Electricity did not make machines smarter. It made them independent. By separating power from motion, electricity unlocked flexibility, safety, and scalability that mechanical systems could not easily achieve. That is why it took over. Not because earlier machines failed, but because the limits they imposed finally mattered.
As machines became electric, something quietly disappeared. Earlier systems exposed their logic. Power could be seen moving through shafts, belts, gears, and wheels. Cause and effect were visible. When something failed, the reason was often obvious. Electricity hid that process. Power arrived silently through wires. Motion began without visible transfer. Machines worked, but their inner logic became harder to understand without instruments. Mechanical literacy declined. In pre-electric systems, operators understood how motion was created, distributed, and controlled. They could trace force from source to output. Skills were tactile, audible, and visual. Electric machines reduced that need. Operators no longer listened for imbalance or watched for misalignment. Diagnosis shifted from senses to meters, gauges, and later software. Understanding moved away from intuition toward abstraction. Repair changed as well. Mechanical systems invited intervention. Parts could be seen, removed, and reshaped. Electric systems relied more on replacement than repair. Faulty components were swapped, not rebuilt. This altered relationships with machines. Earlier systems demanded respect and attention. Electricity introduced distance. Power was present but unseen. Failure felt sudden rather than gradual. Efficiency increased, but awareness decreased. Machines became quieter, faster, and safer, but also more opaque. Users learned to trust outcomes rather than understand processes. This was the trade-off. Electricity did not erase skill. It relocated it. Knowledge moved from the workshop floor to engineering offices, from hands to diagrams, from observation to calculation. Something was gained. Something was lost. And the machines no longer showed their work.
Modern machines did not appear fully formed. They inherited their structure. Long before software, sensors, and electric motors, engineers had already solved the core problems of motion, control, timing, and feedback. Those solutions did not disappear. They were absorbed. Gears still matter. Gear trains that once distributed water or steam power now exist inside transmissions, clocks, engines, and industrial equipment. The mathematics of ratios, torque, and reduction remains unchanged. Feedback systems persist. The logic behind mechanical governors survives in modern control theory. Sensors replaced spinning weights, but the principle is identical. Detect change, correct deviation, maintain stability. Sequencing never left. Cams, drums, and linkages once dictated order in looms and automata. Today, software performs the same role. The instructions are no longer carved in metal, but the idea is unchanged. Structure shapes behavior. Mechanical constraints once prevented machines from exceeding safe limits. Modern systems enforce limits digitally. What was once physical is now abstract, but the purpose is the same. Even failure follows old rules. Wear, friction,
tolerance, and alignment still determine reliability. Electricity removed some constraints, but not the fundamentals of engineering reality. Modern machines are layered. Electricity added flexibility. Electronics added precision. Software added adaptability. But beneath those layers, mechanical logic still governs what is possible. This continuity matters. It explains why machines behave the way they do, why certain designs persist, why complexity cannot escape physics. Electricity accelerated machines. It did not rewrite them. The DNA of modern machines is mechanical, inherited from systems built long before electricity existed.
In an age of automation and software, old machines still have value. Not because they are nostalgic, but because they solve problems modern systems often ignore. Pre-electric machines were designed for constraint. They worked with limited materials, limited energy, and limited precision. As a result, they prioritized reliability over optimization. That trade-off still matters. Watermills, windmills, and mechanical systems could operate without grids, fuel deliveries, or complex supply chains. When conditions changed, they degraded slowly instead of failing instantly. Resilience was built in. Modern machines aim for efficiency. Older machines aimed for survival. Thick components, slow motion, and simple logic allowed them to endure imperfect maintenance and unpredictable environments. They were also transparent. Failure modes were visible. Problems announced themselves through sound, vibration, and resistance. Operators could intervene early, often with basic tools and experience. This is why many pre-electric principles persist today. Backup systems rely on gravity. Emergency mechanisms favor mechanical release. Critical infrastructure often includes low-tech redundancy alongside advanced control. When modern systems fail, older logic returns. Hand pumps replace electric ones. Mechanical valves override digital control. Manual procedures take over when automation collapses. These machines also teach limits. They remind engineers that complexity increases fragility, and that reliability often comes from simplicity. They demonstrate that systems do not need to be fast to be effective. They need to be understandable. Electricity expanded what machines could do, but it did not eliminate the need for systems that work without it. That is why these machines still matter. Not as artifacts of the past, but as lessons that modern technology continues to relearn. When machines failed, it was rarely because they were inadequate. It was because expectations changed. Pre-electric machines were built for a world of limits, limited power, limited materials, limited precision. They were not optimized for speed or convenience. They were optimized for continuity. They did exactly what they were designed to do. These machines assumed scarcity. They assumed interruption. They assumed human attention. As a result, they were cautious systems, slow, visible, and forgiving. Electricity changed the environment. Power became abundant, invisible, and instant. Machines were asked to do more, faster, and with less oversight. Complexity increased, and tolerance for failure decreased. When breakdowns occurred, the blame shifted, not to the system, but to the machine. Yet the underlying logic never disappeared. Modern systems still rely on the same principles: controlled motion, feedback, sequencing, redundancy. Electricity layered new capabilities on top, but it did not eliminate the need for sound mechanical foundations. The difference is expectation. We now expect machines to be flawless, silent, autonomous, always available. When they fail, the failure feels sudden because the warning signs are hidden. Earlier machines failed loudly. They shook, they slowed, they demanded attention. That visibility was not a weakness, it was a feature.
Machines were never the problem. They reflected the conditions they were built for. As technology advanced, we gained speed and scale, but we also accepted distance from process, from understanding, from cause and effect. This is the real legacy of pre-electric machines. They remind us that systems must be understood to be trusted, that resilience often comes from simplicity, and that progress is not just about power, it is about knowing what happens when power disappears.